Good morning, my YouTube viewers. Crystal here. What I wanted to do is I wanted to make you a video, and I wanted to compare a multivariate class imbalanced data set against the sklearn and statsmodels logistic regression. Because you notice that one of my last videos I did, I compared sklearn and statsmodels logistic regression against the binary labels. And what I wanted to do today is I wanted to compare it against a multi-class labels. And I wanted to use the E. coli data set because it's an imbalanced multi-class data set. And so if you can if you can create a model on the E. coli data set and get it to work, then you can probably create a model on any multi-class data set because E. coli data set is imbalanced. So what we'll do is we'll do a code review and go over the code that I wrote for this E. coli imbalanced data set to compare sklearn against the statsmodels logistic regression multi-class. So what we'll do is the first thing we'll just read a little bit about this data set. It says the data set describes the problem of classifying E. coli proteins using their amino acid sequences in their cell localization sites. That is, predicting how a protein will bind to a cell based on the chemical composition of the protein before it is folded. The dataset is credited to Kenta Nikai and was developed into its current form by Paul Horton and Kenta Nikai in their 1996 paper entitled A Probabilistic Classification System for Predicting the Cellular Localization Sites of Proteins. In it, they achieved a classification accuracy of 81%. The dataset is comprised of 335 examples of E. coli proteins, and each example is described using 7 input variables calculated from the protein's amino acid sequence. So, and then they give you the 7 amino acid sequences, and then they give you the 8 classes. So the first thing we'll do is I wrote this program in Google Colab. But because I wrote the program in Google Colab, I transferred it over to my GitHub account, and quite often I'm not able to get the programs to load up on my GitHub account. So what I've done here is I'm viewing the program that I loaded onto my GitHub account in something called Jupyter Notebook. And Jupyter Notebook allows you to view Jupyter Notebooks. So that's what I've done to be able to make this video. So the thing that I've done is the first thing I did after I wrote my program in Google Colab is I have loaded my libraries. And the thing about Google Colab is it's got the libraries already installed on it, so the only thing that you have to do is you just have to import. That's all you have to do when you're using Google Colab. So I imported pandas, NumPy, Matplotlib, and Seaborn. The next thing I did was I loaded the data set, but the data set didn't have any column labels, so I had to assign column labels to the data set. If I did not assign column labels to the data set, what would happen is the row number 0 would have become the column label, and we don't want that. The next thing I did was check for any null values, and fortunately in this data set there were not any null values, so we did not have anything that we needed to compute. The next thing I did was I compared the result with the independent variables. And so there you go. You got result equals train group by result, sum, reset index, and then there's your result. The next thing I did was I label encoded the result. And the reason why is because in most models, they want numeric values. They won't accept non-numeric values. So in order just to make things easier, we went ahead and label encoded the target. So now what we're doing is we're doing the pre-processing. So you can see here where we have label encoded it. So we've got a heat map, so you can see how the independent variables relate to the dependent variable, which is result. And then what I did was I put each class on a counter. So you can count how many hits you have of each class. We've got 8 classes. And class 2 and class 3, you only have 2 examples. And on class 6, you only have 5 examples. So we have a very highly imbalanced data set that we can work on, and we can see if we can get a representation of all 8 classes when we're going through this. So again, what we want to do is, this is again telling you how many instances you have of each class. So class 1, class 0, you've got 142. Class 1, you have 77. Class 2, you have 2. Class 3, you have 2. Class 4, you have 35. Class 5, you have 20. Class 6, you have 5. And class 7, you have 52. And then so what we do now is we give you a percentage of results. And so class 0 is 42%. Class 1 is 23%, class 2 is less than 1%, class 3 is less than 1%, class 4 is 10%, class 5 is almost 6%, class 6 is over 1%, and class 7 is close to 16%. So it tells you what percentage you have of each class. So what we've done now is we've got a graphical representation of the result, so you can see on the graph the representation. So you have like more instances of 0 than you do anything else. And then number 2 and number 3, you don't have hardly anything else. And I think it's the same thing on number 6 or number 7. But so there's your graphical representation. And so now what we've done is we've created a histogram of all of the 7 independent variables. So if you like histograms and you like to see how they relate to one another, you've got a histogram there telling you how all the variables relate. So that's good for people who are interested in analysis. And now what we do is we define our x and our y variables. So your y is train result, and your x is train drop result, axis equals 1. And we check our shape, and you see there's 335 rows with 7 columns for x and 335 rows for y. Now we split our training data set for training and validation using the train test split. And what we did is we set the test size up for 50% because I wanted to try to get at least one example in my in my result, in the outcome, in the output. And then the next thing we do is we scale it. So we put the xtrain and xval in a scalar. So scalar equals standard scalar fit xtrain, and then we transform xtrain and xval. So we put xval on a counter. So you can see how many instances we have of each example in the result. So we'll say class number 3, we only had one. In class number 2, we only had one. So it's going to be very difficult to get to be able to address this class imbalance, which is why this is a good data set to work on, because then we can try to address the class imbalances. And if we can find a model where it represents all 8 classes, then you know you have a good model. But so far, I haven't really found a model that represented all 8 classes, but I still want to go over this code review with you anyway, because you can still find out which model is the best. And what some people do, like Jason Brownlee does, they just say, well, just take out the imbalance, like so number 2 and number 3, you've only got 2 instances of number 2 and number 3. So they would say, well, just remove those rows from the data set. But I don't really want to remove those rows from the data set. And the reason why is because I want to be able to address this class imbalance. And you're not going to be able to address the class imbalance if you're removing the class imbalance. So now what we do is we set up a variable called class weights, and since this is a class imbalance, you can actually use class weights to address the class imbalance. And there's other ways you can do it. You can either do it with class weights, or you can set up a formula with class weights. But what I tried to do when I was working on a binary label, it made no difference if you set it up for balanced or you set it up for the formula for the class weights. It made no difference. You still had the same result anyway. So if you wanted to, you could say class weights equals balanced, but we've just made up a little formula here. You can use that if you want it, but it makes no difference. If you set it up for class weights balance, and it's going to automatically account for that anyway, but I'm using it anyway. So we've got another diagram of y-val. So this diagram of y-val, what it does is it's telling you, how many representations you have of each class. And so you can barely see number 2 and 3 and number 7 as well. They're almost not there, because if you go back to 2, you've only got 1 representation. 3, you've only got 1 representation. And I think there's, let me see, in 6, you've got 2 representations. So now what we do is we define our model, and we're going to do logistic regression. We have multi-class set up for multinomial to let you know that it's a multinomial logistic regression. It's a multi-class imbalance data set. Random state equals 0. Penalty equals none. Solver equals saga. Class weight equals class weights. Max iteration equals 2000. And using that model, I was able to get an 89.82% accuracy. And then I predicted on xval, and I got a 76.79% accuracy. And so I put the result on a counter, and I've got 1, 2, 3, 4, 5, 6, 7. So it missed out one of the outputs. So one of the outputs it missed out. And then you can see when we put it on the confusion counter, you see number 2 over here, number 2, because you've got to remember they start with 0. Number 2 had 0 instances, so it didn't pick up number 2. We put the result on a graphical representation, and you can see here where it didn't pick up one of them. It only has I think 7 representations when it's supposed to have 8. So now what we're going to do is we're going to do statsmodels logic SR model. And statsmodels logic is written more in the genre of R. So people who program in R will be more familiar with this type of code. So logic equals SM, M in logic, Y train, X train, fit, method equals BFGS, max iter equals 100. So it didn't give me an accuracy because I'm new to stats models and I didn't know how to get the accuracy, but it says current function equals 239068, and it says function evaluations 101, gradient evaluations 101. And then we had to do something called XCore because I had problems getting the formulas to work. I couldn't get the accuracy to work. It wouldn't accept it. So it said something about correlation. That was the error message that I got. So I did XCore, and then you see if any of those are 1, it means it doesn't correlate. And we can see that we've got 1s in there. Or it correlates too much, really. And the next thing we do is we predict on our valuation set. And again, it's written a little bit different than sklearn because it says y hat equals logic dot predict xval. And then I just went over to pred because I like pred better. That's what I'm used to. Equals list map np round y hat. And then I said pred equals np array, pred d type equals np n64 because I wanted it to be an integer. And again, because of the output that you get, because you get something called y hat, because of the output that you get, we had to do something else. We had to say pred equals np.argmax, pred axis equals 1, and then pred 1. And then so that means 0. And we got it to work that way. And so we printed the accuracy score, and we got a 79.76% accuracy using that methodology. Put it on a counter, and we had 1, 2, 3, 4, 5, 6. So we only had 6 classes represented on this counter, whereas sklearn's Logistic Regression, we had 7 classes represented. And then so here you can compare the original values against the predictions. So it allows you to do that, and you can compare it if you want, but I prefer to put it on a data frame. df equals pd data frame actual y value and predicted pred. So there's your data frame. So it tells you, again, compares what the actual value was against what you predicted, and I prefer that better. Okay, so then we do random forest classifier, and that is not something that we compared, but we got a much better value on random forest classifier. We got a 1 when we trained it on X train, Y train, and we got an 83.93% when we predicted on the valuation set. So that was really good, but still number 2 didn't get represented. We put it on a graph, and you can see there that number 2 didn't get represented. We tested on decision tree classifier, and again, whenever we put it on the we fit the model on X train, Y train, we got a 1, and when we predicted on the valuation set, we got 76.79% accuracy, which is pretty good. We put it on the confusion matrix, and it still didn't pick up number 2. We put it on a graph, and you can see on the graph well, it says right here, let's see what we've got here. So it says 1, 2, 3, 4, 5, 6. Let's see. 1, 2, 3, 4, 5, 6, 7. So it only picked up 7 and a number 2. It didn't pick up anything on number 2. So that seems to be where they have the problem. And then here you can see the graph that it made. Next thing we did was extra trees. Extra trees, you had, when we trained it on X train, Y train, we got a 1. And when we predicted on the validation set, we've got 85.12%, which is pretty good. And again, it didn't pick up number 2. And so you can see that there, that it didn't pick up number 2. Let's see what it did. It didn't pick up number 2 or number 3 for that matter. We use gradient based classifier. When we put gradient based classifier on the, we fit it on X train, Y train, we got a 1. And when we predicted on the validation set, we've got 79.76%. And again, it didn't predict on number 2. And then so we've made a graph of that, and you can see the representation. We put it on ADA boost classifier, and when we use ADA boost classifier, we got a 1 when we fitted it on X train, Y train, and we've got an 86.31% accuracy, but it didn't pick up number 2 or number 3. So far we're not able to find a model that's going to pick up this class imbalance. Put it on MLP classifier, we've got a 98.20% accuracy when we fitted it on X train, Y train, and when we predicted on the validation set, we've got 79.17%. And again, it didn't pick up on number 2 or number 3. And you can see your graphical representation of that. We put it on a bagging classifier, and when we fitted it on the X train, Y train, we've got 85.03% accuracy, and when we predicted on the validation set, we've got an 80.36% accuracy. And let's see what it did. It looks like it picked up 8. 1, 2, 3, 4, 5, 6, 7, 8. So it worked on the bagging classifier. The bagging classifier was a good model to use. The bagging classifier picked up all 8 examples. So that was a good model to use. So we know that it works on bagging classifier. And when we use bagging classifier, our base estimator was SVC. So that was a good model, bagging classifier. Keep that in mind for imbalanced data sets. We tried Gaussian NB, and we've got 86.82% accuracy when we fit it on X train, Y train, and we've got 80.95% accuracy when we predicted on the validation set, and it didn't pick up on the 2 or the number 3. We picked XGB classifier. We got 100% when we fitted it on X train, Y train. When we predicted on the validation set, we've got 82.14%. And it didn't pick up number 2 or number 3. So that's it. That concludes this this code review that we had. So we know now that the stats models logistic regression doesn't work on class imbalances, and I actually looked it up, and it said that there is no class imbalance for stats models, that it doesn't address that they might get it at some point, but at this present time, they don't have a way to correct for class imbalances. But we do know that the bagging classifier works on the class imbalance. So I think I'm going to use this bagging classifier on another program. So that's going to be the tip for another program, because I know a lot of people are interested in class imbalances because that's something that they really need to improve upon. So that concludes our presentation. If you like my video, please like, subscribe, and share. If you like the work I do and you want to make a donation, I've got my email address to my PayPal account in the description box down below. And thank you so much for watching my video, and I look forward to making another video for you.